I'm Mike Brambley, the lead for the Control of Complex Systems Initiative, which sponsors this lecture series, and periodically we'll be bringing in recognized experts to the laboratory to share insights into the latest advances and applications in the control field. I'm pleased to introduce the lecture series inaugural speaker, Dr. Richard Murray. Dr. Murray serves as the Thomas E. and Dolores Everhart Professor of Control and Dynamical Systems and Bioengineering at Caltech. Dr. Murray is a member of the National Academy of Sciences, and he serves on the advisory committee for CCSI. He holds bachelor's degree in electrical engineering from Caltech and a master's and doctoral degrees in electrical engineering and computer science from the University of California, Berkeley. Again, we are honored to have Dr. Murray here today. Please join me in welcoming him to PNNL as he speaks on specification and synthesis of complex networked control systems with applications in physical, biological, and computational sciences. Richard?
Thanks, Mike. Oh, it's a pleasure to be here. So I'd say a couple of things. First off, this title's not my fault. Mike and I made up this title. We were sitting at CDC and we were setting up this talk and he said, okay, you got to give a talk that, like everybody at PNNL can somehow relate to. So this is what came out of that, sort of process. So that's where that came from. And as some of you know, I was supposed to be here on the 11th of January and got thwarted by the weather simultaneously here and in San Francisco, where it was terrible weather on both ends. So everything was getting canceled. So it's a pleasure to have this rescheduled and be able to come back and talk today. So what I'd like to do today is to talk a little bit about some of the current ideas going on in control theory that are hopefully relevant to the PNNL mission or missions. And talk a little bit about some of the areas of application of some of the existing tools. What is it that control theory can do? Where are some of the places that it can be applied? But also talk about some of the opportunities, I think, in areas at the intersection in particular of control and computer science. And I'll say a little bit about where specifically that is and why computer science. So the way that I'll do that is, since maybe not everybody in the audience is necessarily a controls expert, I'll say a little bit about what controls is, just to kind of introduce the topic, talk some about what the field's been doing over the last decade or two, and then kind of dive into the main technical topic, which is this idea of bringing back together control and computer science, because in some sense they started as information sciences from a similar spot, split for a while, and I think that there's now some bringing back together that can be done. And then end by talking about some of the opportunities going forward. Okay, so let me start by saying a little bit about what is control. So the traditional view of control, which anybody who's taken a controls class has certainly seen, is that control, the idea is to use sensing, actuation, and computation in a feedback loop to provide stability, performance, and robustness. Right? So think about cruise control as the sort of prototypical example. Right? You set it, I drove in from the airport, I set it to 65 miles an hour, it drove me at exactly 65 miles an hour. There were no hills actually, but if there had been hills between here and the airport, it would have held it at 65 miles an hour, right? All of those good things in a very good way. And so the typical applications, sort of thermostats and cruise control and flight control systems and things like that have been around for decades. But I think this is starting to change now, and if you ask people in the field now about what they do and where they apply those things, I think you see a little bit of a different view. And so I like to think about controls these days as a collection of tools and techniques for analyzing, designing, and implementing complex systems in the presence of uncertainty. And complex systems is the same complex systems in CCSI. And it is the combination of dynamics, interconnection, communications, computing, and software, bringing all of that together that sort of defines controls. And the more modern applications of these are the things that are on the right, things like autonomous vehicles. I do some work in biological control that I'll tell you about very briefly at the end. Large-scale networks. This is a picture of the internet, but could just as easily be the power grid. Large-scale enterprise-level systems. This is a defense application, cooperative vehicles, things of that sort. So those are the sorts of things we're doing. And so I would maybe redefine controls as not being about sensing, actuation, and computation in a feedback loop, but maybe talk about controls as the field that thinks about dynamics, uncertainty, feed forward, and feedback. Right? So those sort of four topics combined together in I hope, a useful way. Now, there are a couple of principles that pervade all of control theory, both in the kind of traditional view and in the emerging view. And so these really haven't changed in some sense. We're just applying them in different settings, and you'll see that in all of the things I talked about today. So the first principle is that feedback is a tool for managing uncertainty. If you have uncertainty in your system or environment, by measuring what's actually going on and comparing that to what you want to be going on, you can modify the behavior of the system so that it does the right thing. If you go up a hill, you start to slow down, you say, oh, I'm slowing down, I'll speed up. So you now have made this, right? It is robust with respect to the uncertainty of what the terrain is. And so it is a way to manage that uncertainty. And that uncertainty can be in the environment, it can be in your system, it can be in various components. So that's one. Feedback is a tool for doing that. The second principle is that both feedback and feed-forward are tools for design of dynamics. That is, by integrating sensing, actuation, and computation, we can redesign the way that the system responds to its environment. We can compute what's going to happen, or what do I think is going to happen, what are the probabilities of it happening, and make a decision based on that computation of what's going to happen over the next 10 seconds or whatever it is. We can take the dynamics of something that is undesirable, unstable perhaps, and make it stable. In fact, this example over here is the one I usually use in classes. This is an unstable aircraft, right? The wings are pointed forward. If you tip up a little bit, right, it sort of swings up. But if you put feedback around it, right, you can make it a highly agile, stable aircraft. You can design the dynamics to be what you want. Same with the power grid, same with building systems, right? All of these things, we can design the dynamics to respond in the way that we'd like. Now, these two principles together have a corollary that fits with kind of the theme of things. And that corollary is that feedback allows us to get subsystem modularity and interoperability, and that's what allows us to manage complexity at scale. Right? So the use of feedback around modules says this module will behave in the way it's supposed to behave, independent of what it's connected to, right? Upstream and downstream. And that means that now that modularity lets me build bigger and bigger systems and not have to worry about every component changing the behavior of every other component and having to manage the whole thing at once. I can use feedback to make my system modular. I can use that modularity to build systems at scale. So this is what I think of control theory as being about these days. And so you can see why I think it's relevant to many things going on here and in lots of parts of industry, government, and academia. Okay, so that's kind of my one slide about, what is control theory. So it's traditional view, sensing, actuation, computation, and a feedback loop. More modern view, dynamics, uncertainty, feedback, and feed forward coupled together. Okay, so what are some of the things that the field's been doing over the last decade or two? Well, there are lots of important trends, I think, in terms of what's going on. One that is getting used everywhere these days is optimization-based control. So this little video over here is a flight control system that we built now about 15 years ago at Caltech. And what you're looking at here is a system in which we are computing for the next 10 seconds ahead what we should do in order to fly a desired trajectory, not run into the roof, satisfy all of the actuator constraints, satisfy all the nonlinearities, implementing that for 1/10 of a second, and then recomputing. And then recomputing, and then recomputing. So this is receding horizon control or model predictive control. And we're doing this, right, at a rate of 100 hertz. Now, at the time that we did this, it took a $20,000 dedicated DSP computer to do that, right, that has the power of my cell phone, right? And so, this is just ubiquitous now, right? So if you're thinking about a building management system, you are certainly optimizing over everything you can think about optimizing for the next 2 hours, 12 hours, 24 hours, right? Implementing that for a couple of minutes, checking because your models may not have been right, things may have changed, et cetera, right? You're going to use feedback, right, in that feed-forward calculation and get that to work. So optimization-based control is now, I think, ubiquitous. It's one of the things that gets used in the aerospace industry, in the building industry. It gets used in planning out computation for large server farms, right, all over the place. Autonomous cars, right, all of these use some notion of this, compute out using a model for some period of time, optimize over that, and then recompute. So that's one. A second area that has received a lot of attention in the last decade or so is thinking about the architecture of these systems. So this is an example from the DARPA Grand Challenge. This is the Caltech team in the 2007 DARPA Grand Challenge navigating an intersection. We have to wait until the cars go. Once the cars go, then it's our turn to go. We can start driving. We don't know exactly where the lanes are. We don't have high-resolution maps like the cars today. So we're doing all of this on the fly with the information that you see streaming in from the cameras and driving down the road. And you can see it's not perfect. And so pretty good for a bunch of Caltech undergraduates, though. Come up to the next intersection, see that there's a car there, different level of decision, right? Oh, stop, wait until the car goes. Oh, the car's gone. Okay, now start driving forward, staying in the lane. Stop when you get to the lane line, right? Regulate your velocity. Okay, wait until that car goes. Okay, now I can start going forward. So here there are multiple layers of computing that are going on. The programs that are running that, there are about 200 executable threads running simultaneously on about a dozen cores, right? operating at 3 or 4 different layers of abstraction in different ways. Low-level feedback regulatory loops for things like speed and lane keeping. Higher-level loops for maintaining, do I change lanes or not change lanes? Even higher-level loops for saying, has something gone wrong and I need to take some action like back up in the middle of the road or something like that. So this notion of thinking about architectures and layering is something that's received a lot of attention. Again, in autonomous driving is one of the places that you see quite a lot of that. Another, and it's going to be one of the things I talk mostly about today, is in the application of formal methods for analysis, design, and synthesis. So the video that you're seeing over here is a example where we wanted to have the defenders on the bottom block as things came in. So we call this the robo-flag drill. And so what you were seeing there was, as the defenders came in from the top, there was a distributed assignment algorithm that was running on the bottom trying to say who's going to block who. Right? We actually described that in terms of formal descriptions of what the task was and verified that that worked correctly. It's a hybrid system because you've got the motion of the individual machines as they're trying to block, but you also have the assignment problem and the distributed communication problem. And so that was an example of something there. And I'll talk a lot more about this. Often this is in the area of cyber-physical computing. So if you've heard of cyber-physical systems, this is one of the sets of tools in that area. And the last area where there's been a lot of emphasis, and I think things are getting better. I would say we're not solved or completed with this one yet, is in the area of enterprise scale systems. Right? So as we go from thinking about individual components and things like the cruise control system, think of that as a component level thing, to the overall system, we're controlling you inside of a city and keep autonomous cars, to the enterprise, we're controlling the entire city of Los Angeles' transportation system. Right? What is that going to look like? And so here, of course, the challenges are the increased scale. Smart grid is one of these types of systems that you guys are working here a lot on. This is absolutely an area where we see a lot of integration of software controls. It's absolutely an area where we're going to see a huge amount of increase. The picture over here is a GE picture on the industrial internet, which is one of their initiatives. There are similar pictures from many other companies who are thinking about the Internet of Things. The types of numbers that people talk about are 20 to 50 billion devices on the network, many of these embedded controllers, sensors, actuators, and other things. And so really an enterprise scale system. Okay, so within the controls community, if you go to the conferences and other things, you'll see lots of stuff going on in these 4 areas. There are many more. I picked these 4 as the ones I think, or especially the first 3, there's been huge advances. And that third one in the area of smart grid, I think advances. In some of the other areas, we're a little bit behind, but I think a lot to be done. Okay, so what are the challenges in addressing control for these types of systems? How do we do it? What are the tools that are available? So let me start by just saying, what does the design of a modern networked control system look like? So one of this complexity. So of course we start with some physical system. That might be a car, it might be a building, it might be a gas turbine engine, it might be a chemical process control plant, whatever that physical system is. It has some interaction with its external environment. And typically we're going to design this physical system. And so we'll start doing that design by building a model of both the system and the environment. And then we'll do design iterations on that model, right? How much actuator authority I need. If I need to cool the building down a certain amount of time, how many chillers do I need up on the roof, et cetera, et cetera. Once we have that basic setup done, okay, I have the authority required to implement the control functionality I want, then we start to do some of the lower level control design where we wrap some controllers around that. And so, for example, we'll start putting actuators and sensors on there. We'll process those sensory information with a Kalman filter or some other type of estimation algorithm. And we will probably do some sort of control loop, low level, think proportional integral derivative control or things like that. And so now at this stage, right, we've now got a controlled system, and this may require redesign of the system because now as you start doing that, you may find out that you need higher bandwidth actuators or that you need lower noise sensors or other things. And so we may redesign the system at this point or iterate on that design. But now once we've done that, now we have a module. This module is I can control the temperature in this room to within 1 degree within 10 minutes or something like that. And so now I can think about going up to the next level of the system. I can do that level of control in every room in this building. Now what do I do when I want to manage the overall usage of energy in the building? And so at the next level of abstraction, we start doing things that are at the online optimization level, like I showed you for this little flight control experiment, where we start saying, well, let's optimize over time. Let's kind of do a feed forward, a model-based prediction of what's going to happen, do some optimization over that, and come up with a trajectory that we want, say, the temperature in a room, or the vehicle on a road, or the power of a gas turbine engine to follow. We use more sophisticated online optimization techniques here, things like model predictive control and receding horizon control. We also use more sophisticated state estimation techniques, moving horizon estimation, particle filters, or two, that one can use at that level. And so at this level, again, we can think about, okay, well, now maybe I figured something out, right? And so I might do another redesign cycle, right? So we're going to keep doing this. And then finally, we get up to what we often call the supervisory level or the decision-making level of control. This is where you start thinking about things like mode management, contingency management. Something failed, I need to shut things down in a graceful way without harming the equipment, or some sort of constraint got hit and I need to shift which actuators I use, other sorts of things. Often those will happen up at this higher level. And so there are multiple layers of abstraction that we're designing across in this system. Now, one important thing is that this external environment that's sort of sitting here at the bottom, to some extent has to be represented at all levels of the system. And so really we have to represent it as we go all the way up the stack. The environment is at the decision-making level. When you're at that intersection, right, and you're deciding, do I stop or do I go or when do I go, you have to have a representation of the environment there, right? That same physical system may have something down at the lower level. I'm following a car, right, and I've got to decide how far to stay behind it, right? So we have the external environment entering at all of these levels. Now, increasingly in the systems that we design, they are networked systems, as you can see from the title of the slide. And so we have networking communication. And similarly, networking communication cuts across all of the different layers. It's what allows us to connect these things together, what allows us to get system modularity and subsystem modularity. And that turns out to be extremely important. Now, once you have this sort of an environment, in particular once you've got the network communications going, and so you can really make use of advanced computation because you can put your computation in different places and use a lot more computation, then you start to do some things that are kind of fancier. So for example, you start to use online system models, right? Why just use a system model from when the system was built, right? I've got data about the system. The car's driving, it's got more people in it, the gas tank's a little bit emptier, it's 10 years old instead of 2 years old. I can factor all of those in, right, to my online optimization algorithms. And so we start to see the use of online models of what's going on. These online models then become very reconfigurable. They allow us to optimize based on the current condition, right? They allow us to do trade-off studies and other things. It's like you're moving the control design problem from being a purely offline problem, right? Here's the model, design the controller, right? To an online problem. Here's the model right now, tell me what to do right now. Okay, do it again, do it again, do it again, right? And so those sorts of things can matter, and the online system model affects every level of this stack. Now, the other thing that happens when you kind of enable this in a networked way is you're able to do a lot more computation, not just for the online system model, but for the various components. And so it'd be typical these days that you would run not one state estimation algorithm or one online optimization or one decision-making algorithm, but many of them. These might be at different levels of abstraction, or they might be in parallel under different assumptions. And so you start running lots of computations. I mentioned that on the DARPA Grand Challenge autonomous vehicle that I showed you the video of, we had about 24 cores of processing that was available. And so you can do a lot of computation there. We ran multiple planners, right, and then would switch between the planner, right, depending on the condition or the mode or other things. And so we're constantly running these all at once. Now, as soon as you start running all of those things in parallel, you face another problem, which is the problem of timing. Right? So now all of a sudden, all of these things are slightly asynchronous, right? So think Internet of Things, right? It's not all one big clocked system. And so you have to start managing, right? Okay, one system may see an event at a slightly different time than another one, or two events that occurred nearly simultaneously in the external world might get represented in the opposite order due to sensory processing by the time they propagate up to this layer. So what happens if at the lower layer of abstraction I saw, wait a minute, emergency, stop, and then drive forward, and at the other I saw, drive forward, oh no, wait, stop. Does that matter, right? Are the two confused, right? Maybe one of them switched into a mode and something happened. So how do we deal with that? So that becomes a challenge as well. And finally, all of this is, for a system, right? A building, whatever, but it also connects up to cloud resources, operators, and other subsystems. So this is really the type of control system that we have to design these days. So when you look at what design of a modern network control system looks like and what control engineers do, along with people in many other disciplines, is we think about how do you design systems of this complexity, how do you keep all of these things, how do you pay attention to all the right things at the right time, at the right layers of abstraction, all of those things. So fundamentally, of course, this is still, to some extent, a problem that is one of sensing, actuation, and computation at a bunch of different scales. But as I've already said, I like to think of it more as dynamics, uncertainty, feed forward, and feedback as the driving topics that you have to deal with. Okay, and there are lots of examples of these systems. Aerospace systems look like this, self-driving cars look like this, factory automation, smart buildings, grid transportation. That was on the slide before I came to PNNL, right? I mean, this is the type of thing where these sorts of things come up. And there are also lots of challenges. in getting these. So we're certainly not done, even though we design these systems and we get them to work now. One of the challenges that becomes difficult to deal with is the difficulty of figuring out where these layers of abstraction are. So, you know, what does it mean to be at the lower layer, inner loop, this would get called in control theory, right, versus the optimization layer? What are the interfaces between those? What information do I pass back and forth? One thing I always like to point out is that you don't want to design this all at once. Because if you do that, then the problem is too big. You need to break it up into layers, and you need to have the interfaces in those layers be well defined. And so I usually talk about having contracts, right? That is that the lower layer that's going to implement the regulatory loop should, under some assumptions, give me some guarantees, right, about the performance it's going to do. Now, from the next level higher, I can assume those guarantees, but I need to guarantee the assumptions that it used, because I may be sending it commands on what to do, and if I had some assumptions on those commands. So we get assume guarantee contracts that link the layers. But once I'm within a layer, I just have to worry about what are my assume guarantee contracts down and up. Right? And now I don't have to worry about what actually is going on in the detailed control design or what's actually going on in the detailed decision making. If I'm at that optimization layer, I can think about, good, I have some assumptions about what's going on there, I have some guarantees, that's my design problem. Splitting it up that way is what allows us to build, right, complex systems and manage uncertainty at scale. That's one challenge. Another challenge is that these become very distributed problems. So I think of these as vertical contracts because they're going between the layers of abstraction. But we also have, within a given layer, many things happening at the same time. So think of that as a horizontal contract, right? So at this given layer of feedback control, you've got a bunch of feedback controllers that are trying to control building temperature or trying to control traffic on a network, say a communication network. They're all running at the same time, right? And they also have to have contracts. They have to share information, consensus, and things like that are ideas that come up here. So these are horizontal contracts within a given layer, right? What are the contracts between all of the agents at that layer? And in all of this setting, we have to think about the primary things that we think about in control, that is stability and robustness, but increasingly in these network systems, security and privacy as well. How do we make sure that external agents can't come in and get us to do something we don't want to do? How do we make sure that external agents don't come in and find out something we don't want them to find out, right? Whether those external agencies are just an advertising company who wants to figure out what your purchasing habits are because you're using an online feedback-controlled ad-based revenue system, right? And so how do we make sure that that doesn't provide more information than we want? Okay, so that's sort of, I think, the picture that I like to think about in terms of what these days controls engineers are doing and trying to provide tools. And again, this is with people who do communications and people who do computing and software and the physics of all of the systems, right? All of those things matter. Now, in looking at what's happened over the last 10 or 20 years or so, I do think there are some areas that we haven't paid enough attention to. And so I want to just list a couple of these for you to think about. One is, although I've said a little bit about it, I think we haven't spent enough time thinking about the impact of cloud computing, big data, and machine learning. So scale is certainly present in the things that I've told you about. Smart grid is certainly a large-scale system. The internet's a large-scale system. But I think traditionally within the controls community, we've thought of data as a second-order object, right? You take the data, you process it to get the thing you want, the parameters in your model, right? And then it's the parameters in the model that you actually deal with. The model, you know, the parameterized model is what you care about. But I think in many applications, we want to think about data as being the first-order object. My representation of the system might be the data about the system, right? If I collect all of the data from all of the cars driving in all the United States, that seems ridiculous, right? Until you're in San Francisco and you see the Uber drivers driving around, right? Collecting all of the data, right, in San Francisco, right? Multiple times. Every day I see an Uber car collecting data, right? What are they collecting data on? What are the traffic patterns? What are humans doing, right? You know, how do people react to this stuff, right? All of that stuff. Okay, good. What are you going to do with that? If that's your representation of the environment, right, here's a couple of terabytes or petabytes of data about how humans react to cars. How do I feed that into my control problem, right? What do I mean by stability and robustness in that context? So that's one I don't think we've spent enough time thinking about. Another is this area of security and privacy. Stuxnet was maybe one of the early times that sort of opened people's eyes to the fact that we need security. There have been many since. There were probably some before. This was just one that was particularly noteworthy, where essentially, right, you know, sort of the SCADA system, the control system essentially, was infected in a way that caused damage. Privacy, and you know, people have already talked to me today, right? You know, so if you say security and privacy, and think about whether it matters, right? Privacy is a little bit different, right? If you want to protect information, even if that information might not be used to infiltrate, but just might be used to know something about you, how do you do that, right? How do we make sure that we're not leaking information by people being able to watch what's happening? And so I think that more can be done there. For the most part, right, controls engineers have assumed that nobody's going to want to look at the information and do anything bad with it, and all of the information on my internal buses I can trust, right? All of the commands coming across, et cetera, right? No longer good assumptions, all right? Haven't been for a while. So I think that may change the way we build these systems. A third area where I think we haven't spent enough time in the controls community is thinking about the role of humans and human interaction. So there was some discussion in the past about human in the loop and on the loop in military applications. But when you look at areas like robotics, and you look at the theory that's there to help us understand that interaction with humans, I think it's really just now starting to happen. And so we see this a lot in autonomous cars, and how do you interact with autonomous cars? How do humans interact with you? You start getting these things like, how does a human interact with you when it knows you're autonomous? So I had a student at Caltech who was having a robot that was driving around in a crowded lunchroom, and we were taking lots of data in the lunchroom to try and understand if I move in front of somebody, when will they stop and not stop and do inference on it, right? Kind of data-driven sort of inference. And that all worked great until the people noticed it was a robot and started moving around it and blocking it, right? It's trying to get by and, right, it's blocking it, right? That's not in our data set, right? Because that's not what people do to other people by and large, maybe little kids, right? So anyway, that human interaction, right, how the heck do we put that into our control design problems? Another area that is starting to get some attention, certainly here, is energy and sustainability. Again, I think in the past we haven't spent enough time there. That's starting to change. We see that in smart grid, obviously, building grid types of systems. I think another one on the energy and environment side is areas like geoengineering. So geoengineering is fundamentally a control problem. We all hope that we don't have to go there, but I have to say, based on all the predictions and other things, we're going to have to go there. And so, how are we going to modulate things like cloud cover by throwing particles up in the air, and where do we throw them, and when do we throw them, and how much do we throw to get the right things to happen on the planet? So I think these are areas that could use more emphasis. So these are areas I would say in the past decade or two we haven't spent enough time looking at and should spend more time looking at going forward. So I think the good news of all of this is there's still a lot to be done. So if you're a controls person, right, you've got lots and lots of really interesting things to think about. They're not pure control problems. None of these are pure control problems, right? These are problems that involve economics. These are problems that involve computer science. These are problems that involve various disciplines coming together. And I'll say that multiple times. Okay, so that's kind of control, where we are, what I think the field has been doing. Let me spend a little bit of time diving into some of these ideas about more specifically at a technical level, what can we do in the intersection of control and computer science? And I'll do that by talking about this rapprochement between formal methods and control. This was a title that was given to me by Claire Tomlin. She wanted me to come give a talk, and she said, here's what I want you to talk about. And so I like this title. I had to look up rapprochement in the dictionary to figure out what it meant. I'll let you do that if you don't know. But there's an interesting thing happening, which is that if you look at what control theoreticians would typically write down as a typical control problem, they might do something like this. I've got some process dynamics, I've got some disturbances that come in, I have some outputs that I want to regulate, I may have some weighting function like frequency weights, what are the frequencies that are important to me, and other things. I've got some disturbances, those are often operator-bounded uncertainties. This might be I don't know the flexibility of the wings exactly, or I don't know the dynamics of the building exactly, and so I'll put those dynamics in as some sort of an uncertainty block, again with some frequency weighting, where do I know things, where do I not know things. And the control design problem is to design a control system, this controller down here C, that takes some signals from the system and actuates some of the inputs to the system and satisfy some performance metrics under the constraint of stability. And a typical performance metrics might look something like this. I want the true norm of this signal, so just the integral of the square root of the integral of the square of the signal, this output signal that I care about, to be less than or equal to some constant gamma times the input signal, right? So think about this as the energy of the output should be bounded by the energy of the input, and this gamma tells you how much should I attenuate, right? So if gamma's 0.1, I want disturbances of some size get attenuated by a factor of 10. If it's 0.01, by a factor of 100, et cetera. And that would be the performance specification for the nominal system. I also want to do that when I know that I might have an unbounded operator here. So thought of as an input-output operator, I simply know that it's bounded, and this frequency weight sort of tunes that a little bit. So this is the H-infinity synthesis problem. It was something that's been studied since the 1980s and is largely solved. Now, when we go and look at computer science, one type of computer science problem might look something like this. I've got a process. I have some external environment, right, which I'll label here delta. This external environment is the part that interacts with me. I do something, it does something in response. I have some disturbances. Those disturbances are things that don't interact with me. They're going to do it whether I, no matter how I move, they're going to do something. I want to take the output of my measurements of this process, right, and do some control action. Think about an autonomous car driving, right? And so this disturbance might be red light, green light, other things that, let's say it's just something that's on a timer, it doesn't interact with you. This delta might be the other cars on the road and how they interact with you. You might be measuring your own position, velocity, maybe some things about the cars around you, and you now have to decide how, do I start, go, drive down, change lanes, right? What do I do? And of course, the picture looks like a similar version of this picture, right? Except, of course, what's happening here is these are all finite state automata. That is the way that I describe, right, a traffic system might be I say, well, the car can either change lanes or not change lanes, go through the intersection or not go through the intersection. And so I have a discrete system in a computer science setting. And all of my environment is some sort of discrete dynamics, some finite state automaton. Non-reactive environment, just the things that happen. So is my reactive environment, the other vehicles around me. My process dynamics are going to be a finite state automata, and my controller needs to be a finite state automata. But the problem is still the same, right? I'd like to guarantee some performance conditions under a description of what the environment and system uncertainties are. And so here, it turns out that about now 10 years ago, there was a formulation of this problem in computer science called GR1 synthesis. GR stands for generalized reactivity. And this is a formula that describes the GR1 synthesis problem using temporal logic. And I'll tell you a little bit about temporal logic in a minute, so let's not worry about it for right now. But it is basically the same form as what we had before. That is, it is something that says the environment satisfies some specification, and I want that to imply that the system satisfies some specification. In the standard control setting, the environment was the size of the disturbances and the amount of uncertainty. The system spec was the size of the output error that I cared about. In this GR1 specification, the environmental specification is on the left of the implication sign, and the system specification is on the right. And again, I'll show you more about what that is. So really, this type of problem, where the computer scientists would say, oh yeah, we solved this problem, and the controls people would say, we solved this problem. It's the same problem, all right? And so really, we're solving the same problem, or we're starting to solve the same problem. Again, these results are, on the computer science side, only within the last 10 years. These results on the left-hand side are within the last 40 years, and in a much simpler setting than some of the computer science ones. But one of the things that's important now is, it's not just solving one or the other, but solving both. Right? And so the types of systems that we're talking about for autonomous driving, for flight control systems, for building management systems have both a discrete component and a continuous component, and so we have to solve both of these simultaneously. And there are lots of these types of systems that look like that. Aircraft, plane systems look like that. Autonomous vehicles look like that. The industrial internet's going to look like this, right? All of these systems look like this. So what I think we need to be doing as we start thinking about this class of systems is getting a lot more rigorous about the way we design controllers for reactive systems. And so the systems that we are building are too complex to be tested by trial and error, so we need specifications and we need ways of verifying those specifications are satisfied. They're too safety critical to be tested by trial and error, right? So I do a lot of work in aerospace controls. The spec for aerospace controls is no more than one, so any software, all controls work as software these days, any software package running on an airplane that is in a safety critical function, like the flight control computers, you have to demonstrate as engineers that you'll have no more than one failure every 10 to the 9th flight hours, right? So 10 to the 9th flight hours is 100,000 years, okay? So I don't know about your software. My software is not quite that good, all right? Now, if you take, 100,000 years, that's ridiculous. Obviously, components fail way more often than that, right? So what do? Well, you put in redundancy, obviously, right? So you put in multiple components and you have software that switches between them and you do all of that stuff. 100,000 years still seems like a long time. If you take just the flights in the United States, and you look at how many flight hours there are in the United States in a year, it turns out that once every 100,000 years, in terms of the flight hours, about 30,000 flight hours a year in the United States. Right? So that's once every 3 years, you would have a failure in which people died. That's the definition of a sort of level A failure. Right? And actually, we're better than that, right, at the US level. But if you think in the world, right, about every couple of years, right, an airplane falls out of the sky and people die. Right? And so it is about at that level, and often it's a kind of weird software problem interacting with a human, et cetera, et cetera. So this is about where we're at, right? But to do that requires an enormous amount of effort, and the types of tools I'm going to tell you about I think can help do that. Okay, so another thing that I think we need to think about doing, and again I'll talk more about this in a second, is we need to move from a design then verify to what I call a specify then synthesize. That is, what we do right now is we design it and then we do tons of testing, right? So we just had a lunch conversation, before lunch about, sort of testing and using certificates and other things to simplify testing, but we still simulate or test like crazy to make sure that it works. I think there's a little bit of a different way to do it, where instead of here's the specification and here's the model, now, sort of design it and test it. What if we say, here's the model, here's the specification, synthesize, right, the logic that controls this. And again, I'll tell you how to do that in a minute. I think we also want to think about how to synthesize the specifications themselves. So we can not only synthesize the logic that implements the specification, but we can think about the design problem as a synthesis problem, right? What should the contracts be at these different layers, for example? Can I synthesize those contracts? What's the language that I would use to do that? So I think there are lots of interesting directions there to think about. And then, as if that's not enough, I think there are things that link back to some of the areas that I said before that we need more emphasis on. So how do we think about data-driven methods for doing this? How do we think more about human-like interactions? And of course, how do we include security and privacy as guarantees in this framework? So I think these are all areas in this kind of combining of ideas from control theory and formal methods where the two of them together can do very powerful things. Okay. So now, what can we actually do? So let me tell you a little bit about, from a kind of control theoretician's point of view, some of the things going on down at this layer and what we can do there. And so I want to maybe talk just a bit about temporal logic. If none of this makes sense, it's okay. I'll come back and pop back up to a higher level in a second. But the symbols that I've been using come from a mathematical language called linear temporal logic. There are three operators that sort of matter in the context of what I'm going to show you. One is this diamond, which means eventually. So the way to think about linear temporal logic is you have a sequence of events. And so here's an event occurs, an event occurs, an event occurs, an event occurs. If I say eventually A is true, that means this proposition A, which says something about my system is operating correctly, or I have made it through an intersection, or whatever it is. If I say eventually A, what that means is in this sequence of discrete states, A may be not true, so this means not A, not A, not A, but at some point in the future, A will be true at least once, and then after that, I don't care. So if I say that I have a specification that says eventually A, that means at some point in the future, A will be true at least once. Similarly, this always operator, the square or the box A says always A. That says that A, this proposition, should be true at all future points in time. I don't care about what happened in the past, but if always A, at this point forward, it's always true, right? Forever and ever and ever. And of course, what gets interesting is when you start to combine some of these things. So for example, we can say things like always eventually P. Right? So if P is some proposition, always eventually P is what's called a progress or a liveness condition. It means you do something over and over and over again. Why? Because it's always true that at some point in the future, P will be true. Right? So now suppose P becomes true and then it becomes false after that. That's fine as long as always at some point in the future, P becomes true again. Right? So P has to be true over and over and over again in order for always eventually P to be true. You can flip it and say eventually always P. That says eventually it's the case that P is true and forever after stays true. Right? It might not be true now, but it will eventually be true and then it'll stay true. That's like a stability condition, right? Eventually you'll get within 1 meter of the center line of the runway and stay there. Right? If that was what P was, 1 meter of the center line. And there are various other ones that you can put together to do that. So linear temporal logic is a nice language for talking about some of these discrete systems, discrete state systems. We use a variant of linear temporal logic in the work that we do that's called signal temporal logic. Signal temporal logic allows real variables instead of just continuous variables. It's a set-based thing, though, so not super complicated. But I can say some voltage needs to be less than the maximum voltage, for example, in signal temporal logic. But more importantly, I can put time bounds on my operators. So this one says that it's always the case that between time t1 and time t2, P is true. Outside of that bound, I don't care. This one says that if P is true, that should imply that between time 0 and T, so 0 seconds from now and T seconds from now, Q will eventually become true, at least once, right? But in those time downs. So metric temporal logic is a similar type of thing. Signal temporal logic, these are basically the same ideas. So this is a natural mathematical language to describe these. Most controls engineers don't know linear temporal logic. Most computer scientists do. Most computer scientists don't know about H-infinity control. Most controls engineers do, right? So this is this combination. So let me just give a really simple example. If I look at something like a stoplight, I might have in that stoplight a finite state machine, right, that controls which color goes which. And so here might be a finite state machine. And so if I'm green, then I go through to yellow, right, and I go to red, and then maybe, you know, I'm green, and then at some time I go yellow, and then after some time I go red, and then I may wait until I see a car come up in the other direction, right? And you can tell this is in Europe because I go to red, yellow, right? So in Europe, you'll turn the yellow light on first, right? And then go to green, right? And so, you know, this is an example that's coming from some guys in Europe. So there's a simple finite state system. What are the types of specifications I might write down? Well, for example, I might say, I would like this stoplight to always eventually turn green, right? So it should be the case, right, that in each direction, really, it always eventually turns green. Otherwise, not a very good stoplight, right? May as well just put, you know, sort of block the road, right? Another one might be that I want it to be the case that it is always true that if the stoplight is green, then it will not be red on the next step, not next red, right? So this little circle is the next operator, right? This says that I can't go from green directly to red, right? You have to go through some period of something else. Doesn't say, this spec doesn't say yellow, right? It just says you can't have green be true and then red be true. In this case, there's no other choice, right? But, oh, all the lights could go off, right? This doesn't stop you from doing that, right? That would satisfy this part of the spec. Here's a little bit more complicated one. This one says it's always the case that if the light is red, it will eventually turn green, and it will not turn green until yellow, right? That's Europe. This is a spec for Europe, right, that says that if it's red, eventually it's got to go green, but it also has to be the case that it's not green until it's turned yellow first, right? And again, this is you know, not something that's not a spec for the US, right? And you might synthesize a different. This finite state machine actually wouldn't work for the US, would not satisfy the US spec, satisfies the European spec. So these are some simple examples of how you write down these sorts of specifications in this language. Now, the reason to adopt this sort of formal approach is that it turns out there are a ton of great tools for doing things. And so one of those tools coming from the computer science community is model checking. So the idea of model checking is I give you a system, a finite state machine, that can go in different ways depending on different events and other things. And I give you a formula. This is actually a formula from an electric power system for aircraft that we worked on. And then I would like to know, do all possible executions, that is all possible changes of state that are consistent with this diagram, satisfy this formula or not? And you can imagine this would be a hard problem because I have to basically enumerate all possible things that could happen, and then for each one of those things, check every possible thing. But the model checking community, the computer science have gotten really good at this. And so there are ways to do this. And so this is from that same book that I pulled the example from, Bear and Katoon, showing how, the kind of block diagrammatically, how a model checking system works, where you have a system description that you model as a finite state automaton. You have a property. You actually negate this property. And then what you tell the model checker is, I believe that this system will negate this property. And then it goes and tries to find something that dissatisfies the property, right? If it finds something, that's a counterexample, right? Because now I've made your property be not true, right? So one of two things happens at the bottom. I either tell you no, and I give you a counterexample, really good for engineers because they always think their designs are right. So you say, no, but think about this. And they go, oh yeah, damn. All right, I go back and think about that, right? Or it says, in all of the possible executions of this, right, it will always satisfy this property. I could find no counterexamples, essentially, right? And I exhaustively searched it. I don't exhaustively search it by enumerating them all. I do much smarter things than that, and that's what all the blocks down here are doing, is giving us the technology that we need to do much smarter things. Okay, so that's what a model checker does. Modern model checkers check all possible execution traces, and they can work with quite large state spaces. Actually, this is a little bit old. 10 to the 9th discrete states now, 10 to the 10th, 10 to the 11th discrete states. Pretty big, right? If you think about the number of possible discrete states in autonomous cars, probably in those numbers, right? We can model check things of that complexity. Spin and new SMV are two that are particular ones that we use. And so the idea, of course, is given this technology, right, we want to leverage that for system design control. This exists, right? This is something you can go off and just download the tools and run them, right? Both Spin and new SMV are free tools, right? They're available. Okay, so how might we use these in the context of control design? Well, so the idea is we have a system model, we have some assumptions, this is on the unknowns, how the environment's going to behave, other things. We have some requirements on the system behavior. We basically boil those down to a system and environmental model as a finite state automaton, and a set of formal specifications as an LTL formula. The verification problem is, given a controller that is supposed to satisfy the specs, take the controller plus the system model and the formal specifications and verify either that it's satisfied or it's violated, and if it's violated, give me a counterexample. The problem that we were interested in is one that's called logic synthesis. And what happens there is you say, look, you gave me the system model and the formal specs. Can I just synthesize the finite state machine that automatically satisfies the spec? And this is, if you're a controls person, this is like LQR, right? I give you x dot equals ax plus bu, the system description. I give you the quadratic cost that I want to minimize. And I say, synthesize for me, right, the controller that stabilizes the system and minimizes this cost, right? This is the same thing. Here's the system spec, here's the specification, synthesize the logic that does that. So, and this works in the sense that I will either synthesize a controller that satisfies the spec, or I will tell you no such controller exists. Your spec is actually not achievable, which is nice to know, right? Before you get out there and you're, get the sudden acceleration problem on your car or whatever, right? And then you find out that, oops, right, something went wrong. Okay, so this is an area called logic synthesis. It's very powerful. We can make use of logic synthesis for solving our control problem. And I'll do this just in the discrete setting, but there are ways to connect the continuous and the discrete. So here is my discrete problem setting. I've got a process, I've got an environment, I've got a controller. These are all finite state automata. And what I want to do is I want to say, for all possible executions of the environment and the process that satisfy these finite state machines, find an execution of the controller, that is, react to what the process and the environment did in a way that guarantees that some spec, not written here, but some LTL specification is satisfied. So that problem you can formulate, and it's got one little problem, right? It is doubly exponentially complicated in the size of the system spec. Right? So if you had 10 specifications, it takes you 2 to the 10th nanoseconds to solve. Right? But if it has 100 specifications, it takes you 2 to the 100th nanoseconds. That's longer than the life of the universe, so we're done. Okay? So just, sort of, in fact, probably, it doesn't take many more specs. How many specs in the systems that we all look at? Hundreds of specifications, right? Very complicated. So that's why nobody's doing this, right? Because it doesn't work. But something changed. I've already told you the thing that changed. There was this GR1 synthesis technique. That is, if you look at formulas of a certain type, it turns out that those formulas make some additional assumption. One is that I can view what the environment does before it reacts to it. So this is a fast enough type assumption, right? The car starts to turn, I can see it can turn, and I can make a decision right before it changes its mind and stops turning. So not too terrible, but breaks the symmetry on all the problem. If you make that assumption and you look at formulas of a certain sort, then what happens is that you can now kind of unwind the problem. So the environment does something, the controller sees that, the controller makes a decision, implements that, the process and the environment both take their step, then so the process takes its step, then the environment takes a step, I see that, the controller does its. When you unwind all of this, you can solve that problem. And it turns out that for a certain class of specifications, you can get things that are cubic in the number of states to describe the system. Cubic, right? This is like telling you that, some optimization problem is convex. Right? Oh, solvable. Or it's actually better. It's like telling you it's like a linear program. Oh, solvable big, right? I can solve big linear programming problems. All right, so this is only a result from 2006, right? It's about 10 years old. So, right, this is something that made a huge difference. And it turns out that the class of specifications, won't surprise you, is exactly this class, right, that I've written down here as an environmental assumption and a system guarantee. And the environmental assumption is that I have to have some rules that are always satisfy the environment and some liveness conditions, so always eventually, I told you about that. And that should imply that my system has some safety conditions that are always satisfied and some liveness conditions. So if you can put it in that format, and any of these can kind of go away, meaning you can remove any of them, there are various generalizations, then it's a GR1 spec. And so GR1 really just changed the game in terms of what we can do, right? So these general reactivity formulas meant that we can suddenly solve big problems, or interesting problems. All right, so let me just give you an example, and then I'll kind of wrap up. So here's an example of a problem. We saw this a while ago, but it's still one of my favorite examples, so I still use it. So DARPA Grand Challenge, right? You're driving around, right? And here's the spec for this problem. You're a car. You want to drive through these two starts. You're like a bus, right? This is your bus route. You're going to go through these two intersections over and over and over, right? So the spec's going to be something like always eventually go through here and always eventually go through here, right? Over and over and over again. And you have to satisfy the rules of the road. You have to stay in your lane. You have to stop at stop signs. You have to give the right of way, right? All of that stuff. So there are a bunch of rules, right, that are the normal traffic rules. You can't collide with other vehicles. Stay in your lane, right? Only proceed through intersections when they're clear, things like that, right? So just, California or Washington State Driver's Handbook, right? Sort of write all that down in temporal logic. Now, you need some assumptions about the environment too, right? So for example, I need to assume that an obstacle can't block the entire road, right? Because otherwise, obviously, I can't, complete this anymore. I need to assume that an obstacle can be detected before the vehicle gets too close. Otherwise, I can't, guarantee that I won't run into it. If you're blind, right? I mean, what could you do, right? So I have to have something there. Here's one that's kind of weird. Obstacle does not disappear when the vehicle is in its vicinity. Where does that come from? Right? Well, that comes from trying it without that and seeing that the system gives you a counterexample. Right? And the counterexample is you're driving along, you see a car in front of you, you move, you change lanes, you get out of your lane, and when you get out of your lane, this car just disappears. Right? Now what happens? I'm in this lane, there's nobody over there. Right? Why am I in the opposing traffic lane? Right? That violates this guy. Stay in travel lane unless there's an obstacle blocking the lane. You go, well, that's dumb. Obviously, it can't just disappear, right? But we didn't say that, right? So the system came back and said, here's a counterexample. You go, oh, yeah, right, okay. In other words, all of these, right, there's actually a whole page of these things, right, come from things like that. Right? I mean, here's another one. Each intersection is clear infinitely often. If you don't do that, right, then it comes back to the counterexample. Says, car goes to the middle of the intersection, sits there forever. You lose. Okay, yeah, but I mean, you know, that's not the case I want. If that happens, right, I'm going to turn around and go home or, right, call the human and get him back in here or something like that, right? So one thing is it forces you to be explicit. Okay, so turns out everything I've written here and the many pages that are behind it can all be described as exactly this type of system where we have finite state automata, we have a GR1 specification, and we solve it. And I'll show you what the solution to that looks like. So I'm going to show you an animation, and what I want to tell you about this animation is that the logic and the trajectories that the car is following in this animation, it's obviously a model, were completely synthesized. We did not do any design. We just gave it the specification. And we gave it the system model, all right, you know, here's what it means to drive on the road and turn your wheel and all those things, and then it synthesized both the continuous controller as well as the discrete controller to do this. Okay, so here we come, the red things are obstacles. When we see them, we drive around them. They disappear because we lose them out of our sensor range. We come into the intersection, there's a car in the middle. We know always eventually that intersection is going to be clear. Once it's clear, we drive through. Remember, we're trying to go through here and here. We come up to this sign, there's nobody there. We turn right, boom, hit that point, come around, see an obstacle, drive around the obstacle, come back in, right, come back to the other point. This time there's no obstacle, so we come back around, right? And obviously we're just going to now go around the circle over and over and over again. Okay, except something happened, right? All of a sudden, right, this red thing, right, you know, semi-truck turns over, right? You know, probably it was the auto truck filled with beer and it got confused, right, and it sort of flipped over or something like that. And so now, right, the whole lane's blocked. Well, obviously, right, I'm kind of messed up, right? But I had over here, right, I said that an assumption was an obstacle may not block an entire road. I mean, I should probably change my slide so it says an entire road. This is violating the assumption. So now what do? Well, you actually pop to a higher level of abstraction. Right? Say, hey, new contingency, road blocked. Right? What do? Oh, well, if the road's blocked, you're allowed to turn around in the middle of a road, right? Even if normally you couldn't, right? I mean, that's a reasonable thing. So I'll change the spec. Right? I'll now say, oh, you can turn around. Right? Resynthesize. Right? Resolve the problem, do it again. In fact, one of the things we're doing in this problem is we're not solving this ahead of time. We're actually solving it online. We're solving it online. Why does that matter? Because our system model, our system specs can change and we can react to those things. Right? So this one, and it's sort of the numbers are here, we actually solve the problem looking forward about 10 meters in about 1.5 seconds. And so we're just resolving, right? We're using this trick of, right, receding horizon control, right, to solve this problem, but at the logical level now. So we can do that. Okay, so we change the rules, we resynthesize, we do all of that online. Once we resynthesize, say, fine, you can make a U-turn in the middle of the road, come back up to this intersection, go through. Now we're going to go around the other way, right? So we go around, we see some obstacles, we go around the obstacles, etc. So you get it from here, right? Okay, so that's an example of all of these techniques working. Okay, so that's the type of work that we've been doing that's at this intersection of computer science and control. There are many other things that people have been looking at. You know, it's just one example of many ways that we can combine these ideas. I think there are other very interesting ones in areas like security and privacy, right? So security is a controllability problem, right? How do you make sure that someone does not have controllability of your system? That is, they can't make the system do whatever they want, right? Privacy is an observability problem, right? How do you make sure that from a certain set of outputs that people measure and maybe no knowledge of your inputs, they can't back out what your internal state is? Right? So there's another area where I think there are things. Security and privacy, not easy. A natural language to write security and privacy assumptions and guarantees is in things like temporal logic. Right? Because you want to be able to say, right, that I'm going to assume that you don't get to watch me forever, that occasionally you don't get to watch, for example, right? So that would be something that you'd write a temporal logic formula, or that you can only see certain things certain times, right? Various assumptions about what's reasonable as your attack model. So I think it's another place where you see that. Okay, I want to just spend 2 minutes talking a little bit about other places where controls comes up, and this is because I know there's some people here who do biology and synthetic biology, and it's something I do as well. So I just one chart on a little bit about synthetic biology. So there are also, I think, non-traditional areas of control. Here I've talked about what I would consider traditional areas of control. All right, these are cyber physical systems and other things. But there are a lot of high-risk, long-range applications of control that are interesting. One that I've been interested in for a while is thinking about biological systems. So here's the next robot that I want to build, right? We built some self-driving robots. I now want to build this robot. This robot is 1 micron long. You're seeing all of the subsystems, right? It has an energy input subsystem, known as a gas tank on a car, but we're going to extract energy from our environment in, sort of a 1 micron long artificial cell. It can sense things about its environment. It can export things out to its environment. Maybe that's for bioremediation or other types of things. Maybe it's a communication mechanism to communicate with other cells. It can move in its environment. It's got actuators of that sort. Inside, right, it's got a bunch of things to do the energy conversion process to signal things from the outside down into the regulatory and computation loops and other things. So this is a control system that I want to design. And it's different because the sensing, actuation, and computation mechanisms are different. These are molecules binding to each other and protein expression and other sorts of things. But really, it is the same in that we have a bunch of subsystems. They're highly uncertain. We need to manage the complexity of this system, right? This is what the field of control brings, is ways of doing that. And so, let's see, we're now probably 14 years left, I think, for me to do this. So I've set a goal for myself 6 years ago that I'm going to do it within 20 years. That's about when I retire. And so I've got about 14 years left. And so by that time, I'd like to really design a 1 to 2 micron long robot. It's not a living thing, right? It's something I design and build when I put it in an energy source, just like I put a battery in something and it drives. I take the energy source away, it stops. That can find a toxin and neutralize it, or assemble chemicals into food, right? The one I often talk about is, geez, what if you could make like a machine that would suck up chemicals from the ground and then turn it into this round orange thing that you could peel and eat, right? I think that's possible, right? It must be possible to do, right? So, okay, can I design it? Not yet, right? All right, so I'm not sure we'll get to orange trees in, that time. And by the way, they ought to grow, here in Richland too, right? And in the winter, why not, right? As long as, what the hell, we can put antifreeze in there and all that stuff, okay. So, drive your car around, right? Okay, so just to kind of show you a little bit of that, this is what a proportional controller looks like in that sort of language. This is work of Victoria Shao in doing a proportional controller that allows you to have the input is this reference RFP, the output is this GFP, and she was able to design a system in which we were able to have the YFP at the output actually track the RFP at the input, and this is showing a dynamic trace of a proportional controller where it's trying to maintain a 1 to 3 rate or 4 to 1 ratio of the inputs to the outputs. Right? So it's an example of that working. And the control sort of picture that goes along with this looks something like this. You have a bunch of process dynamics. These are the core mechanisms within a cell: transcription, translation, degradation, sequestration, other things. You have nonlinear coupling between these, like binding of proteins to DNA and other types of things that have nonlinear characteristics. You have an interconnection matrix: what connects to what, which proteins, what pieces of DNA are in front of what DNA. You have delays that are due to the process dynamics. And as you interconnect all of these together, you have unmodeled dynamics, you have external disturbances, right? What you get to design is the interconnection matrix and the delay matrix for the most part. Right? And so it's a control design problem there as well. And these might be subsystems or broken into subsystems that's distributed, et cetera, et cetera. Okay, so with that, I'll stop. I've told you about a bunch of stuff, mainly on this top row, talking about the overlap of control and computer science, a little bit in the last 2-3 minutes about this bottom row. I think there are a couple of takeaways that I hope you'll take with you. One is that control is about dynamics, uncertainty, feed forward, and feedback. Another is that it's a set of tools for managing complexity at scale. And the third is that there are lots of opportunities, lots of challenges, and I think there's a critical need for partnering with other disciplines. So I've said this a couple of times to people in the morning. This is not something where the computer science community is going to solve the autonomous driving problem. The controls community is going to solve the autonomous, no, right? It's going to be both of those communities and many more coming together. And so with that, I'll just put up some of the people who sponsored our work over the years, and thank you very much for your time and attention.
We probably have time for one short question and one short answer. Any question?
No promises on the second part of that.
Perhaps I can ask a quick one, very quick one. It's a communication, control, and computing.
Yep.
These are the three tools that were applied for the control complexity. We see a lot of computing and control, but what's the view on the communication?
Yeah, I think there are lots of ways that you're going to have to think about the way communication is going to play a role. I mean, we talked some about 5G networks, for example, and what the delays look like, and right, what delay tolerance looks like, and what packet retransmission looks like, and things like that. That will affect the controls, right? And so I haven't said a lot about it, but you're right? Often I'll say controls communications, computing and networking, right? And these are interrelated to one another. But absolutely the role of communications and modern communication technologies and, how are you communicating, et cetera, if you have multiple redundant channels, all of those things, definitely have to be fit into this, right? Not the part we've focused on so far. You violated the assumption, so I can now violate the guarantee.
Mine's more of a popular science question. I was wondering what some of the sticky problems that remain in the self-driving vehicle world are that you're still trying to solve, and where you see the public rollout of self-driving vehicles unfolding.
Yeah, so there are many. The one that worries me the most, that I think is one of the most challenging, is reasoning about human behavior. So, I think the problem of having 90% or more of the cars be autonomous and driving in cities that have been designed for that, right, with pedestrians that know that's what's happening and just stay off the roads, is not hard to solve. The really hard one is 10% of the cars are autonomous. People, bicycles, kids are all over the place, right? And how do I reason about what's going on? And of course, machine learning and big data are going to solve all of that problem, right, most of the time. But the problem is going to be that we're going to have to get used to as a society. We will have fewer accidents, but the accidents will happen not at the hands of humans, right? And so we're usually willing to say, you know what, they made a mistake, right? They feel terrible about it, right? They couldn't have done anything different. You don't say that about a car and a computer, right? You say, whoever designed that car, right, owes me my kid's life, whatever it is, right? And so I don't know how we're going to do with that. And by the way, the car is going to make mistakes that look really stupid to a human, and it's going to do things that humans make stupid mistakes on, and it won't make mistakes. It doesn't get distracted by texting, right? It doesn't, have the sun glint in its eyes and, right, different set of failure modes, right?
Well, isn't that what happened with that?
Yes, but, and I should say, and there's a long way to get there, right? So, you ask, eventually that's what we're going to be able to do. That was a solvable problem, right? Poor...
You gotta work out the mischievous teenager who's intentionally trying to subvert the car.
Well, and I know the car's going to stop, so I just stop, it's 90% cars, I just ignore traffic lights, right? I'm a human, right? They have to stop for me, it's required, right? Yeah, sure, right? Until it's going too fast to be able to stop, or it turns out that one's driven by a human, right? Or something like that, right? So I think that interaction with humans, that's the part that's going to be best. Is somebody paying attention, not paying attention, right? Got their eye contact, what the hell does that mean, right?
We have another event coming in here right after us, and so I'm going to have to end the questioning. I hope you'll join me again one more time and thank Richard.
Thanks.